so we talked about how to test a transformer, right? I think the first day and stuff, and we talked about the disconnect. I want to talk about three things today, and the first thing would be a contactor and a relay, y'all. A contactor and a relay. Now, first of all, at the heart of a contactor or a relay is an electric magnet. And this is a good example of one right here. Come on, y'all see this? There's a lab sheet up over here. We'll grab on each. So that's all this is, right? We got two places to connect, in this case, 24 volts to, and the wire goes around, and we would put, like at home, when we were kids, we'd use a nail, but here we'll use laminated steel. And what that means is you take a piece of steel and you slice it like a deli sandwich. And you take it and then you turn it, that way that it doesn't get aligned. If we don't laminate the steel, let's just say we take a chunk of steel, we melt it down. When the magnet, the electricity's on it, when it's a magnet, it'll still be a magnet. But it'll tend to, it changes the atomic structure in there where all the things that make it a magnet in iron, they begin to line up. And once they do, when you cut the power off, they stay magnetism. Have you ever done that with, say you took a battery, say you remember the old D's, and you wrapped it around, or maybe they were C's, I can't remember. The bigger ones that go in flashlights and stuff. And you take it around your nail, you pick up paper clips, but when you finish, sometimes it would still work. That's because it was a magnet long enough for it to line up the dipoles in there. That's what makes it. Well, if we laminate it, they can't line up, because what we don't want is to cut the power and the magnet stays on.
You got power.
Yeah. So, everybody understand what this is? We call it a coil. And we wrap it around a laminated iron core to create a stronger magnet. This will work right here with just a piece of steel in there. And then so the more coils, the more power, the more iron, we can make a bigger and bigger, stronger one. But so these are designed to do what we need to do at 24 volts. That lab sheet up there for a minute. So this is the heart of our contactor and our relay. And to test this, first of all, why would this work without voltage? It shouldn't. And so the first test you're probably going to get is, do I have 24 volts on there? Because if you think it's working, it shouldn't work if there's not. There's a problem if it's working. If it's on and there's no voltage, we got a bigger problem. So first thing I'm going to do is I'm going to test the 24 volts. If I do have 24 volts, it should be a magnet. And so you can look and say, hey, is the contact closed or is the contact open? Whatever it's supposed to be, it's supposed to change. They already passed one around behind you. So that's the first test. Do I have voltage? Now, if that coil breaks, if you took a knife tip and cut it, it's not going to work. And so when you ohm it out, instead of having measurable resistance, we'll have OL. So it's bad. Now another thing is, this, and y'all see it, now this is a relay, right? I got two relays. This one has tape around the coil. That's the same coil y'all just looked at. Relay. This one's got it's a relay, but it's got a smaller one in there. It's just a smaller one. And these are contacts. And you can see they've got the same coil in there. This one's got tape around it, right? You can see the top. When the magnet comes on, the magnet pulls down a plunger or pushes up a plunger that was under a spring, and we call that the armature. And that armature either closes or opens a contact. Now, wherever, on most contactors, we want them what we call normally open. And normal, you don't have to say that. You can say power off. That's what normal means. When the power's off, where is the contact? So on this, it's open. This is the normally open contact, right? When I give it power, what should it do if it's normally open? It should do the opposite. Just instantaneous. When it comes on, it should switch. When it goes off, it should switch back. On a relay, we often have normally open, which means with the powers off, they're open, and normally closed. Y'all follow me? Normally closed. And when it energizes, what do? The opposite, that's right. The closed one's open and the open one's closed at the same time. These are what we call general relays. And they're not specific relays. In other words, they're not sold and designed and manufactured to do any one specific job. If I told y'all to run down to Johnstone and buy a potential relay, that's what we call a specific relay. It's made to do one thing at a certain amp draw. If I told you to run down there and get your current relay, that's a specific. But these are stuff that we might use on a heat pump for the reversing valve or something. Or we might use this on a blower motor, called a blower motor. We could use it. Some people might say, hey, I would call it a fan relay, whatever. See what I'm talking about? It's a general relay we use to do something we need done. There are contacts out there that you can buy that have closed contacts that open. That's not the difference between the two. You could go, well, contactors only have normally open and relays have normally open and closed. No, that's not correct. You just hadn't been exposed to them. Most of the contacts we use are normally open. They tell us the only real difference is how many amps they can handle. They usually say relays are only used up to about 20 amps and contactors used above that point. And some textbooks might say 15. You know what I mean? That's not written by God, so who knows? But basically, if you're talking about a lower amperage, it's a relay. 60 amps on a contactor, okay? They work the same way. So, but we can have voltage at the coil. Can somebody let him see that coil?
It says 60. If it's 60,
If it's above 20, they're going to call it a contactor.
above 20 is a contact.
Yeah. So if we have voltage at the coil, what we're saying is all this is a little electric magnet. You connect 24 volts to each side of that, and it wraps around, and what's missing is an iron core. And that iron core would complete the magnet. So when we have voltage at the coil, and the coil is working, in other words, it's not burnt out or broken, it creates a magnetic field that should open or close the armature. Well, that armature can break. Anything that moves can break, right? Move apart. And so just because we have 24 volts and just because you owned it doesn't mean the armature could have stuck or it could have welded shut, it could have spring could have broken. So we can have both kinds of breakdowns. So we see how to test that, right? If I apply voltage and it doesn't change position, it's bad. Now, let me just say a little bit. I'm going to pass this one around. It's a relay. Then I'm going to pass this one around. And then finally, I'm going to pass this one around. And I want you to see the difference. Now, like I said, we would use these things to accomplish what we want to accomplish. Now, I'm going to start with this one. Before you pass it on, I want you to look carefully. And when you look at it, coil. And they gave us 2 positions to make that coil. And if you look very careful, because it doesn't say coil, you can look at it and see where underneath a little bitty tiny wire feeds down from it and goes to this coil. Is this a new one? You could connect to this one or this one, right? They're just giving us a place to make an easy connection. Anybody got a question like, should I use the top one or the bottom one? Doesn't matter. You need 24 across it. Now at the very top, we've got 2 levels. And if you look carefully at it when it's coming around, there's a raised piece of plastic that separates it. So it has 2 identical circuits. These stake-on connections, I have one here. Is that what it looks like? So this will connect to here, normally closed, here, normally open. And then pretty much an identical. Does everybody see that when it's coming by there? This one does not connect with this one anywhere. I mean, you could choose to if it helps you. These don't connect with either one. These control a magnet that either close these or open those at the same time. They cannot be closed at the same time. They can't be open at the same time. They are going to swap. Now, terminology. Well, I'm going to call this one when we're talking and you say, hey, Clay, then I say, hey, test this. I'm going to call this normal open contact. I'm going to call this normally closed. And the one that connects to both, I'm going to call common. Does that make sense? Not fancy. What would this one be? Close. What would this be? And these 2? What would we call these? Coil. Okay, so that's the first one. Now, that one costs the manufacturer a certain amount of money. A certain amount of money. And the person who bought it or the company who put it on their equipment paid a certain amount. Now, here's one. Anyway, there's a stake on stick on there. Except for this one, the coil doesn't have 2 to hook to it, it only has 1 on the bottom. Does that make sense? Take a look at this. There's something missing here. Alright, what have they done? They've said, hey, carrier, I'll sell you these if you don't need this. Carrier said, hey, I don't need a normally closed contact on this unit. So we can save you 20 cents or something. Well, that's all they care about. They could buy the other one and have it and not use it, but they're into saving money. So you might go, well, what's the difference? Well, they just didn't do it. You can tell it's set up at the same mold, you know, the same plant, the same machine makes it, except for they must have some kind of function not to do it. Now finally, this one here is a little cheaper. And you have to read on the side, like those had it etched out, right? Did everybody see the etching to show the circuit? All right, so this one here is numbered 1 and 3. That's my coil. Up here I've got 2, 4, and 5. And so if I look at the thing, it says, okay, so what does this mean? All right, we understand what the coil means. If I apply 24 volts there, it's going to make the normal change. In other words, if it was closed, it'll open, open, close. So what they're saying here is 5 and 4 right here is closed. It's normally closed. If you need a normally closed, there's a normally closed on here. If you apply voltage here, this is going to go up here and close 2 and 4. Now the same factory that makes these, and if you look at that one, all you see is this. But that's what's going on inside the shell. But the same factory makes that one can make it separate and not tie these two together internally. But that's not what we have in this case, but sometimes you do. Now, let's talk about this for a second. I'm going to put these back here. All right, let's say I wanted to bring my blower motor on. And so I send a 24 volt R to the thermostat. And the thermostat, somebody goes fan on, click. That passes power to the G terminal. And so I would run the G terminal 24 to here. And I would need to run 24 volt common back to the transformer common. So when the thermostat did this is going to close, right? And so I could take line voltage and run it into the common. And I could have a neutral over here. And I could have me a blower motor over here. And I could run off the normally open contact to bring that blower motor on. Could I not? Thermostat energizes, closes, lets power flow, and I'm running. You can see why we had to use that normally open. But let's say that this furnace let's say that we're not always planning on the customer. Can I answer?
My car blew up and he gave me a ride. Can he just sit?
Sure.
He's waiting on me because I have a
it in heat to go, you know, I was supposed to put the fan on. So the blower motor won't run. So let's say this was high speed. Instead, I could use this same relay to come off the normally closed. I could run it through a temperature switch mounted in the furnace so that every time it sensed, say, that the furnace got to 100 degrees, then it would close. And I could run that to bring on maybe my low speed. So this would be an example of, we may need the normally open and the normally closed. We may even need a duplicate set. We often use a duplicate set when we're dealing with emergency heat on strip heating. Okay? Do you think y'all know how to test these? First, I want 24 volts at my coil. Well, that's the lab, but I'm just saying in the future, 24 volts at the coil. If you don't have it, why should it work? If I do, and it's not working, it's not opening or closing, depending on what its contacts are set at, I can own the coil out, right? What's my two rules with owning? Enough power to isolate one of these sides. If it owns out what means it's good? Measure resistance. It's bad at what too? OL or zero. And so if it measures good, then maybe we need to check the contacts. Are they closed and open? Because we could have an armature problem. Okay? All right, so that's what I wanted to cover on relays and contacts. Okay? Now, let's talk about testing motors. Now, if you have me for circuits, you've already seen this. So here I have a condenser fan motor, 1 speed. That's kind of simple, right? So always, you know, a motor is just the opposite of a generator, really. And so here, I'm going to put me a magnet or two. Let's just start with that. That'll be simple enough. How do I create a magnet? Iron core. Wrap it around an iron core. Right? I got a magnet. So we're going to put these two in parallel. Over here, probably need to go over there. Wow. So here I have a magnet. So all I have to do is put a conductor in the middle here, a rotor. We call these magnets our stator. And when this magnet lines up, it's going to push-pull based on the repel of that magnet. And because we're using AC voltage, the power company is nice enough to change the direction, the polarity, a whole lot every second, right? Every time it goes around that generator to change the polarity. And so these poles are going to change, plus, minus, or north and south, whatever helps you think about it. And it's going to push and pull and repel this motor to make it work. Now, the weak point of this invention is getting it spinning. Getting it spinning is the hard part. It's locked. We call it a locked rotor. It's not spinning. And so, we pretty much use what we see a PSC motor, permanent split capacitor motor. So we would label this winding, wires in front of this, as the main, or we usually just call it the run. Okay? On a permanent split capacitor, we add a second set of windings or poles. Okay? And really, this is, in a lot of books, even if it's not a permanent split capacitor, it's what we call a split phase motor. And so, I'm just going to add another set of magnets here. And bearing in mind, we may have 6 or 8 of those. And let's start here. But it's the same power, right? Well, I didn't really say if I had 120 or neutral or 2 hot, but we have at least 2 different levels of power intensity there. So, how is this any different? Because the wire we used on the run winding was thicker and shorter. And the wire we used on the start windings, that's right, thinner and longer. So when we start an electron race, this was going to finish first. It's going to be positive and then negative and positive and negative before this will. And that'll knock us out of phase. And so that creating out of phase gets us spinning. Now, the way the voltage runs through the start winding, in other words, you notice I came here, I was in the same sequence, that's the direction of the rotation. And so if you have a motor and it's got 2 wires, 2 yellows and 2 purples, and it says change it to purple yellow if you want it counterclockwise or lead in or shaft in. All they're doing is changing these wires to let the power flow in one first and out the other. Okay? So, on our phase race, we have a run winding, right? We have our start winding knocking it out of phase. And we also add a capacitor here. Okay? Power would need to come from one capacitor. Okay. And what do we say a capacitor does? Stores energy. But that takes time. And so we use that time phase to move us even further out of phase. While the start charges and discharges, we're getting farther out of phase to help make these give us more starting torque. Now, we call these a run capacitor, okay, because it always is on when the motor's running. They're usually metal. I'll have one around here. And they're filled with liquid so they can dissipate heat since they're running. Whereas a start capacitor, we could add a start capacitor. Same signal. Is solid inside, much stronger, usually in black hard plastic, and doesn't dissipate heat, and so if it stays on, it'll blow. And so a start capacitor always has have some mechanism to open it up. And we typically use a potential relay in air conditioning because of our amperage. I got a 3-ton compressor. We usually say about 7 amps a ton, so 21 amps on running. Okay? If I tried to run that off of current relay, that's a lot of amperage. That's 60, 80 amps. That's a lot of power. So we usually use a current relay on small fractional stuff like in refrigeration, and we use potential relay, which will work off of voltage for start capacitors. Now, we've already talked about how to test the capacitors, haven't we? You've got a meter, and we tested them, didn't we? All right, so if the motor's not running, right, you know how to test it. First of all, it's got to have voltage. Why would I think it would run if it didn't have voltage? Proper voltage, right? We said plus or minus 10% of its rated voltage. If this is 120, we need to be plus or minus 10%. If it's 208, 230, whatever it is, got to have the proper voltage. We know how to check the capacitors. So the only last thing is, how do I check the compressor? Pardon me, the motor. So we're going to check the motor. This is a single speed, and you can see here, well, I don't have a information data sheet here, which will tell you what these wires are, but I can just about tell you the black one's going to be common, the purple's going to be run, and the brown's going to be start. So what am I talking about? All right. Know what I told you? This is red, run. So as many magnets are in there, the purple wire is going to connect to those. I told you these are start. The brown wire is going to connect to as many of those magnets are in there. But they both have to come back here. Right, to a common size. And so what we have, I guess I can write on this. It's something like this. Say I have L1 here for my common, L2 to my run, L2 to my start. That does not connect. I did not mean that connected. So just like we've been doing, that means to test this thing, I want to use my ohm meter. What are my 2 rules to use my ohm meter? Cut my power off and isolate, right? So I want you to ohm from run to common. If it's good, what are we going to get? Measurable resistance. If I run from start to common, what am I going to get? That's right. If I read from start to run, what am I supposed to get if it's good? OL or 0 is bad. And some of you who use the computer have already found that this can also go to ground, right? That's bad. That would be bad too. We don't want any path back to ground. Now, the one exception is inside this thing, if it gets too hot, we have an internal overload in here, where it's off of thermal. And so how this really connects is, that's my thermal. This thing can open up, right? Actually, yes. If it gets too hot, it breaks this leg. And you all seen that on the diagram. This compressor can get too hot, and I can get a reading from run to start, but I can't get from run to common or starting time. And if you have that, you want to, feel it. Is it hot? If it is, give it either time to cool off. If it's a compressor, you might can hit it with water, and I wouldn't suggest that with a motor. But after it's cooled off, if this doesn't close, she's dead. Okay? Alright, so I got you a new lab sheet in here, right? I'd like you to turn that in before you leave. You can. You finish it. And I know y'all have tested all those components every day. I want you to add some motors out here. Okay, we got plenty of them out there. Do them. Most of them are probably going to be good. It's when you get into multiple speed that you start getting confused. But we're still looking for what? Measurable resistance. Okay, any questions?
Okay, if that gonna get hot and it opens, does that mean, what would cause that besides it not being needed?
Maybe I had bad voltage. I had low voltage or high voltage into it. Maybe it's starting to go bad mechanically, and it's under a bind and it's working too hard. Now I'm not saying because it's overheating and it cools off, it's going to be fine. Maybe somebody laid a pizza box on top of it, and it ran until it couldn't take it anymore, and it popped off. They do reset, but once you mess them up a few times, they don't reset.
So you have to replace the compressor in that case?
The whole part, because I've got some out there I can show you that's open. They're stuck in the windings, and they're tiny. They're about the size. They're a square, maybe they're not exactly square, rectangular. They're about as thick as a nickel, and about the size of a nickel, except for a little small. You can punch out a square out of it, maybe a dime. And when you look in there, you can if you look around, you can see where it's implanted in there. But we can't have a spark, especially in one of these motors in a compressor with refrigerant gas or whatnot, and the oil. So this thing is enclosed, and there's no way you can. It's not serviceable. Pardon me, I should just say. All right, now everybody knows we're not having class Monday, right?
Never,
Isn't that right? This is
right?
I thought you said you're gonna be here in those offices.
Yeah, I said that. Let me stop recording. Hang on.